this question is actually a little easier than the ones we did yesterday. So if you guys can get started on that, I got to run to the library and grab the other people. So I wouldn't put a question like this on a test for this reason. There's not enough to do. There's literally one very simple calculation and this question is over. Okay, but I'm going to walk you through how you get to that simple calculation. All right, so it's asking how much work is done. All right, so we got to remember then that work is a change in mechanical energy. It's also force times distance, but I don't have the force, so I'm kind of cooked on that one. Okay, I got to look at the change in mechanical energy part of this. Now, this is an important part of the question. What does it tell me? The kinetic energy doesn't change. Okay, so when I'm looking at this whole thing and I'm expanding it out, okay, and I go, all right, so this will be my kinetic energy final minus my potential energy final, okay, or sorry, plus my potential energy final minus my kinetic energy initial plus my potential energy initial, okay, I got to look at this and go, it doesn't ever change the kinetic energy. So a change in kinetic energy isn't important because it doesn't change. All that changes in this question is the object's potential energy, because it starts at the bottom of the ramp and goes to the top. Now, because it starts at the bottom of the ramp, how much potential energy does it have there?
0.
Right. Holy smoke, my work is equal to my final potential energy. That was quick. Right? If I'm talking this through, I can really limit the amount of work and calculations I have to do as long as I realize this tells me nothing's changing about the kinetic and that it starts at the bottom of the ramp, so it started with literally nothing. Okay? So the only work that was done changed the potential energy. That's it. So I just go work equals m times g times h final, and I'm done that question. Okay? That's why I wouldn't put a question like that on the test, even though from an intuitive perspective, it's a good question. Maybe good for like a multiple choice question, but not good for a written response, because there's not enough here for me to mark. But good for a multiple choice kind of question. Subtle enough? Okay. So all we had to do was go 80 times 9.81 times 7. That should give us our 5,500 newtons. Okay. Everybody with me there? Now, had there been friction, would this have been a little bit more involved? Yes, because then there would have also been work against the force of friction and so on. Okay. No. No. Okay. Let's talk about the kinds of energy here, because we need to go over that a little bit. Okay, so we'll talk just about, this is just quick review, okay, of energy stuff here. So gravitational potential energy, okay, you have gravitational potential energy if you are above the Earth's surface, or above any surface where gravity would pull you back to the surface. Okay, that's what gives you gravitational potential energy. By the way, you also have to have mass, but that's kind of a foregone conclusion, as all things have mass. Okay, so if you have mass, and you're at a height above a surface where gravity would pull you back, you have gravitational potential energy. Okay? How much gravitational potential energy is dependent on those three things. How much mass you have, what the acceleration due to gravity is, and how high above the surface you are. All right? So it's kind of like this, right? Like if you're looking at a piano and a volleyball, and they're on the top of a roof, right? Like one is going to have way more energy on the top of that roof than the other, even though they're both in the same place. Okay, so gravity's the same, the height's the same. The piano can do way more work because it's so much bigger, okay, than the volleyball. All right, with that idea, they would be going the same speed when they get to the ground in a perfect physical world. Okay, but one has more mass, so thus it has more energy. All right, now Similar situation. If I put that piano on the moon, would it have less potential energy at the same height? It would, because gravity is less. All right, so those are the things that affect your gravitational potential energy. Mass, gravity, height. All right. Questions there? All right, we don't need to do that because I don't think we can do that one either. All right, let's have you guys try question number 1 though. Okay, so a pile driver is not the wrestling move, although the wrestling move does closely resemble what a pile driver does. Okay, so a pile driver is just a big weight that you lift up and then drop. Okay, and you drop it onto a piling, which is what they use to, go below the frost line so buildings don't shift. Okay, if you've ever seen a house built, you can usually see them in the garage portion. They're just round concrete columns, okay, and they're in the ground. If you build a deck, you have them in pilings. Okay, so in some buildings, the pilings are actually driven into the ground by dropping a big heavy weight on them. So that's what a pile driver is, and it's driving the weight into the ground, or the pile into the ground. Yes. Okay, so let's have you guys try question number 1 here. We know the mass of the pile driver is 550 kilograms. It's being dropped from 12.5 meters, okay, above the ground onto the top of a pile that is 2.30 meters above the ground. The pile driver going all the way to the ground. Okay, so keep that in mind. Okay, now it says relative to ground level, so that means 12.5 meters. Okay, what is the gravitational potential energy of the mass at its highest point and its lowest point, and what's the change in that energy if the mass is lifted from the top of the pile to its highest point? So you're doing 3 calculations, all of them pretty straightforward. Okay? Remember that potential energy equals mass times gravity times height. Okay, give you a minute on that one. Oh, shoot, I left that recording. Okay, so let's do this one quickly here. So at the highest point, okay, we have our 550 kilograms times 9.81 times 12.5 meters. Okay, that's all there is to calculating the potential energy at the highest point. Okay, at the lowest point, 550 times 9.81 times 2.3 meters, because that's where it sits when it's on top of the pilot. Right, and then what's the change? Well, I subtract those two numbers, and there's my change. Okay, everyone all right with that? Okay. Okay, try number 3. Okay, so in this one here, the winch is pulling this 250 kilogram block up a 20-meter long ramp. It doesn't mention if it's accelerating it, and it doesn't matter because the question specifies it only wants the change in gravitational potential energy. So, is the gravitational potential energy dependent on the length of the ramp or the height of the ramp? The height of the ramp. Doesn't matter how I get something to the top of a ramp, it has the same amount of potential energy when it gets there because it's the mass of the object, gravity, and the height that matter. So I need to calculate the height of the ramp. So I need the opposite side. So I go sine of 35 times 20, and that'll give me the height of the ramp. So it's 11.47 meters. Now that I know that, since the block started here at the bottom of the ramp where it had no potential energy, all I need to do is go 250 times 9.81 times 11.47, and that'll give me my potential energy at the top, which is also the change in gravitational potential energy because it started at the bottom. Yes. Okay, does that make sense to everybody? Right, so it's a wordy question, and when you set it up, it can look intimidating. But when it came down to it, we did one trig calculation and m times g times h. Okay, so energy questions you really have to talk through so that you don't miss the fact that they might be easier than you think. Okay. All right. All right. Let's talk kinetic energy. So kinetic energy is energy you have if you are what? Moving. Yeah, you don't have kinetic energy if you're not moving. And kinetic energy is dependent on only two things: mass and speed. And we talked the other day about the effect that speed has on your kinetic energy. It's exponential, because V is squared in the formula for kinetic energy. So, the more massive an object is, the more kinetic energy it has. The faster it's going, the more kinetic energy it has. So, is it possible then to have something very small have the same kinetic energy as something very large? Yes. It just has to be going very fast. Okay? This is actually the principle behind one of the kind of modern weapons that weapons researchers are working on. It's called a railgun. Anyone ever heard of a railgun? Okay? So a railgun is it's kind of like a science fiction thing almost, but they're actually working on it, and actually I think had a prototype built. It's a non-explosive projectile, okay? And it's fired not by using gunpowder, right? Most of our modern weaponry is I launch an explosive projectile by blowing something up to launch it, okay? Put a cannonball in a cannon, right? That's the simplest form of artillery. So the idea behind the railgun is you don't have any explosives, and you don't have to have any explosives to launch it. You use an electromagnetic coil. So a whole bunch of coiled magnets that amplify consecutively that just force this metallic projectile out the end of the gun, out the barrel of the gun. But when it goes out, it's moving incredibly fast. Okay? Like we're talking near relativistic speeds. So really, really, really fast. Okay? And it's basically just a chunk of depleted uranium. Something big and heavy. Well, not so much big and heavy, but just like heavy and metallic. Okay? But it doesn't explode. It does all its damage because of its kinetic energy. It's just going so fast that it rips a hole in whatever it hits. Okay? So the advantage, if you're using that as your weaponry, is if somebody hits you, you don't have all this explosive ordnance on board to blow up. Okay? Most ships of war are sunk because they get hit and their own weapons blow up inside, and it blows the ship open. Okay? If you only have these weapons on board, you don't have that worry. Okay? You might get hit, but at least your own bombs don't blow up on you.
It just requires a lot of energy.
It requires
So far.
huge, yeah.
That's why they haven't like really moved it on towards mobile, is because they can't figure out like.
Yeah. They
are
basically
gonna be
need the
able to
nuclear stuff.
carry around a big massive battery pack in order to power
Yeah.
the electromagnetic fields.
Exactly. But the principle is there. If you don't have to have a lot of mass if it's going really fast. Okay? That sort of makes sense? It also makes armor essentially useless. Okay? This thing's just going so fast, it doesn't have to blow up to pierce the armor of another, ship or bunker or tank or whatever. They're just going so fast, they just rip right through. Okay? The sort of conventional warfare was, if you wanted to break through armor, you had to have a shell that had 2 explosives. Okay? So the first one would detonate when it hit the armor, and that explosion would break the armor, and the secondary bomb would go through the hole it made and then blow up inside. Okay? That's a bunker buster. That's how kind of those work. Well, that's 2 different explosions, and that's a lot more gunpowder and explosive that you have to keep sitting around somewhere to blow up on you. Right? This would just go, well, I'm going really fast, so see ya. Okay? I'm just going to go right through whatever. Okay, I don't know if you guys ever saw this. I don't have a video of it, unfortunately, where Mythbusters tried to vaporize that car, okay, with a rocket. Right? And they said, if we can get it going fast enough, when it hits this concrete thing, there won't be anything left of it, because it'll just be going so fast and have so much kinetic energy that it'll just essentially vaporize. Okay? And they were able to do a pretty good job of it. They only found like a few parts here and there. But when the thing actually hit the concrete, like you saw this cloud that was the same color as the car, and then there was really nothing. Okay? There were like itty bitty bits and pieces, and the thing they ran into was like destroyed. Okay? It was a mound of dirt and concrete and whatever, and this rocket sled was just going so fast that it literally obliterated the car, the sled, and the hill it was hitting. Okay? It was just that much kinetic energy. All right, so as we said before, okay, kinetic energy is related to how massive something is and exponentially how fast it's going. Okay.
Demolition Ranch, I think also has like a handheld wheel.
Okay.
It's like really small, and I think like right now it only shoots like little like metal pucks.
Okay. Oh, well.
But it's like supposedly he has like some company shipped them like a prototype.
Well, we'll have to check it out sometime. Okay, so in this question here, guys, can I get you guys to just copy this one down? Because this is going to show you the kind of relationship between something's kinetic energy and how fast it's going. All right, so we've got a car that has a mass of 1,200 kilograms. Okay, and its speed is 20 meters per second. And then we have a van that's 4,800 kilograms, so 4 times the mass. Okay, and it has the same kinetic energy as the car. We're looking for the speed of the van here. Okay, so just from a common sense perspective, is the speed of the van faster or slower than the car if they have the same kinetic energy? Slower. Yeah, because it's more massive, right? But it might not be as, like, the speed might not be what you expect, okay, in this case. All right, so really, all we have to do here is say this. 1/2 the mass of the car times the speed of the car squared equals 1/2 the mass of the van times the speed of the van squared. Agreed? It said they have the same kinetic energy. So rather than like calculate the kinetic energy of the car and then put it in a formula with the van, I can just say this because it's also true, right? What happens to the halves? They cancel because there's a half on each side. All right, I'm trying to find the speed of the van, so I'm going to divide both sides by the mass of the van, and then I'm going to square root to get the speed of the van. All right, so I'm going to have the square root of 1,200 times 20 squared divided by 4,800. Oh, what's the square root of 100? 10. Okay, so, not 10 squared, 10 meters per second. So, it's got 4 times the mass. To have the same kinetic energy, it has to be going half as fast because speed has an exponential relationship with kinetic energy. So if I've got 4 times the mass, I better have a lot less speed, right, in order to have that same kinetic energy. So that's a little bit, that's something to think about, right? Something's barreling towards you on the road, okay, and it's got a lot of mass. It probably has a lot of kinetic energy, and you should try to avoid it, generally. Yeah. All right, questions on that one? Okay. I'm gonna do that. Okay, let's talk about number 2, and then I'm going to have you guys try question number 3. So, in question number 2, we've got 2 different cannons. Okay, the first cannon fires a 1.5 kilogram ball at 550 meters per second. Cannon B fires a cannonball that has 1/3 the mass, but twice the velocity. Which one would be better at destroying a fortification?
The one with more mass. Wait, is it?
The smaller one. Which has a bigger effect on your kinetic energy, your mass or your speed? Okay, so here's what we want to think about. Okay, cannon A fires this ball. We're just going to say it's a mass of 1. Okay, and it's moving at a speed of, let's say, 1. Well, in the second question, for the second cannonball, sorry, we're saying that its speed is its mass is 1/3, but its speed is double, which means not double, but actually the effective double is 4 times. So I might have 1/3 the mass, but I got 4 times the speed. Well, 1/3 of 4 is still greater than 1. Yes? Okay, so the smaller ball, because it moves at a greater speed, is actually more effective at damaging the fortification because it would have more energy. Has less mass, certainly, but it can go faster, and speed is more important when it comes to your kinetic energy. Okay, sorry, Deacon, question?
So, like, I guess it really depends, though, because if you're more like after a size enough, like, let's say you're shooting this through a concrete wall, and you want to be able to go through the wall.
Mm-hmm. The smaller one is still better. They're not exploding.
No, I know, but like in terms of like, you'd still, actually technically, wouldn't it kind of be the same, because you still have to shoot them the same amount of time?
No,
in order
I
to
would
get
need
a
less.
sizable-
I would need less of the second ball. The second ball has more energy, and the only thing that can damage the fortification is the kinetic energy of the ball. And the second ball has more kinetic energy.
But you need to widen it, which means you'd have to shoot it like.
Nope, I just said damaging. And the damage is caused by the kinetic energy.
So you're
I
not-
get what you're saying. You're saying if I have a big ball, it makes a bigger hole. Maybe, but
No, but-
I'd have to shoot more of them.
Exactly, like. it's
Of the bigger
same-
ball, not the smaller ball.
No, because of the smaller, because if you're trying to get,
But it's not as simple as I'm just trying to punch a hole. Okay? Like, that's not what we're saying here, Tegan. We're just saying the kinetic energy is the only thing that can damage the wall. The smaller ball has more of it, so therefore it's better.
yeah, but I agree with you, I'm just saying, if you were to, like, if you wanted to go through a wall,
I would use
and
the
the only
smaller
way
ball.
to get through it was by, shooting a smaller or bigger ball, and you want the hole in the wall to be the same size as about you so you can fit through it,
Smaller ball.
I don't think the smaller ball
But you have to
has
shoot
energy
them,
to damage
you have
the
to shoot
wall.
them both with the same.
But it would.
No, I mean the bigger one probably.
No, the bigger one would hit it, but not cause the wall.
It would, like, maybe ripple it a little bit, but yeah, the smaller ball would go through it.
Exactly.
But you
And
have
then,
to-
because it's gone through, all the wall that it's taken out isn't there to support the upper part of the wall collapses. The big ball hits the wall and doesn't do anything, the wall doesn't collapse.
But I mean, you still have, like,
But I don't.
you have that size of a hole that you're gonna have to. fit
It's
in.
still a hole. It's more than the other ball did. It's still a hole.
At most, you're gonna be.
I'm sorry, Tegan, you're not gonna win this argument.
He's literally the physics teacher, man.
Okay, let's try number 3. I get what you're saying, Tegan, I totally do. I'm just saying, when it comes right down to it, it's still the smaller ball. It's still gonna be better. Okay, even though the bigger one, you're right, if it got through, would make a bigger hole. Problem is, it's not gonna get through, because it doesn't have the energy to get through.
No, but I mean, like, it's kind of hard to explain, but I know.
Okay, so for the crater here, so this is Meteor Crater in Arizona, okay, and it has a radius of 40 meters. Actually, that's not. Meteor Crater in Arizona is way bigger than that. Okay, so this is a 40-meter wide crater, and the mass of the asteroid or meteor that hit it was 2.6 times 10 to the 8 kilograms, and we have the speed, but it's in kilometers per hour. If we want to get the kinetic energy, we're going to go 1/2 times 2.6 times 10 to the 8 times, what was our speed in meters per second?
20,000.
20,000 even? Squared. All right, so we do that calculation and we get that that is going to be 5.2 times 10 to the 16 joules. Okay, is that a lot? It is. It's a lot. So, the destructive potential of most things, like let's say bombs, nuclear weapons, things like that, are always measured in tons of TNT. That's our units for destructive yield. Okay? To give you an idea, the bombs dropped on Japan at the end of the Second World War were in the range of 1 to 2 kilotons. That means they had the destructive equivalent of dropping 1,000 tons of TNT onto that one spot. Okay? So if you play Minecraft, you can imagine how. Okay? Now, this is the amount of energy released when 1 ton of TNT explodes. All right? So what they want to do is they want you to calculate how many tons of TNT equivalent was released by this thing hitting the Earth. Okay? So we take our 5.2, we take our 5.2, and put brackets, and we divide it by the explosive yield of 1 ton, 4.69. Okay, and we get 1.1 times 10 to the 7 tons of TNT. So that is 11 megatons. It's 11 million tons of TNT. That's a lot. It made a crater 40 meters wide. Right? So you can imagine what a modern nuclear weapon, which would have its yield in megatons, okay, could do were it to be detonated. And they're not detonated by hitting the ground. To maximize their explosive potential, they are detonated at altitude so that the destructive wave dissipates over a wider area than if they hit the ground and make a big crater. Okay? It's actually more destructive to detonate above the ground than to actually detonate when they hit the ground. Okay? Unfortunately, there are people out there who study stuff like that and figure it out. Scary world we live in.
That's megatons, and you said the other bombs were kilotons?
Kilotons.
So, okay.
Yeah, our ability to destroy crap has really increased over time. Yeah.
Wait, what bomb made the 40 millimeter?
This is a meteor that made a 40-meter crater.
Oh, okay. I thought you were still talking about Hiroshima.
No, no.
Okay.
And those were also like airburst weapons. Yeah, that's why there's no crater. It's just
Yeah, because it was nuclear warfare.
all right, we will leave it there for today, guys. Tomorrow, we're doing a lab, and we're going to be doing a lab on the conversion of potential energy to kinetic energy on a card on a ramp again. Back to card on a ramp again. More of that. Okay? All right, hey, if you're going anywhere at lunch or when you go home today, remember that our outside environment is a prime example of physics working against you at every turn, especially on turns where the coefficient of friction may be low and you will have to be aware of Newton's first law. So drive carefully because physics,